Hi folks, there is an issue that I always struggled with when I used the Catia's native FEA solver to solve uh, laminated composite problems. And this deals with the fact that when you're using shell elements to model laminated composites, you have two choices of specifying material properties. One of them through the 2D orthotropic feature, material selection, and the other one is 3D orthotropic feature. And I was always puzzled by why do you need both of these? And I'm going to try to clarify that in the context of an example that we're going to be doing. So let me move to the slideshow mode. Okay, I'm going to do that in the context of this problem. So we have a 300 millimeter by 100 millimeter long uh, rectangular laminate, but it's made of two plies, two plies, 1 millimeter each, and one end of this laminate is clamped, and the other end is subjected to an in-plane load of 1,000 or 10,000 Newton per meter. Okay. Now this is made of two plies. The first ply is minus 45, second ply is 45. Okay, uh, because I can explain these in the context of a very simple case. We don't have to make a very complicated laminate stacking sequence. And these are symmetrically placed about this reference surface. So the 45-degree is above the plane, above that reference plane, and the minus 45 is below. Okay, so I'm going to do both of these problems, okay? And once I show you how to do both of them, then I'm going to switch from the CATIA screen to my PowerPoint presentation. So just show you this for now. If you define the orthotropic material, there is 9 numbers that you have to specify, and these are written here. There is 3 Young's modulus in the 3 directions, which Katia calls it X, Y, Z. Okay, and then there is 3 Poisson's ratio and 3 shear moduli. Okay. For this particular problem, I'm going to assume that, of course, I'm dealing with unidirectional fiber, and the cured thickness is 1 millimeter. Don't worry about these things because we're not using it. Cured thickness is the thickness of laminate. Okay, so I'm going to come back to this screen later on. Right now, I'm just going to ignore it. Okay, so we're going to come back to these later on. Let's go ahead and make our part. So start with the part file and part. I'm going to call it 3D ortho. Of course, the geometry is the same for both cases. So, uh, but I'm going to call this 3D ortho because I'm going to do both models in its entirety. Okay. So on this on this horizontal plane, I will sketch a rectangle which is 100 millimeter by 300 millimeter. So the length of this is 300 and the width of it is 100. Okay, exit and fill this thing with a, I have to be in uh, generative shape design, of course, to deal with surfaces. So I'm going to fill it with a surface. There we are. And I always have a habit of joining these because it gives you more control over the direction of the normal to the shell element. Flip it. So my direction of join is down. So the normal to the shell element is going to be upward. Not that you may not care about it, but anyway. So that's what it is. And let me create a coordinate system here too, which I'm going to be using as rosette. So I'm going to ordinarily it's put at this corner. Okay, so I'm going to move it a little bit to the left so that it doesn't clutter the screen. So in the y direction, I go create a point, a coordinate minus 330. It's going to put the origin right there. and I'm going to say okay, but make sure that this is unchecked because I don't want this new coordinate system to be my actual what did I do here? Okay, something didn't go exactly as I planned. So let me see now. Oh, the origin is going to be okay. Let me cancel that. Delete this. Okay, let's try it one more time. Okay, and this I'm going to delete this point too. Okay, delete this. All right, so let's do one more time. I didn't expect this thing to happen. So origin, create a point, minus 30. Okay, so we say okay. So it puts it there, and fine. Something didn't go the way I planned it last time. All right, good. Now let's save this thing. So file, save management, save as. I have a folder here. Desktop, something called videos right there, and I'm going to put it in the 3D folder. So there we are, it's in there. Okay, then I want to create my material properties. Of course, I can use one of the default stuff in Catia, but I don't want to do that. Okay, so I'm going to close this, and let me show you where I put the file that I created. This is the part that I created. I'm going to put the 3D material in there too. Okay, so back to Catia, file, no, start, infrastructure, and material library. And this is the new one that I'm going to create. So I can say double click on this, double click on it. There's nothing in it. I'm just creating it. First of all, the name, I'm going to make it material. Okay, how about calling it 3D ortho, 3D orthotropic. Okay, and under notice that if you say apply, change the names right there. Composite 1 millimeter, fine, 1 millimeter cube thickness, and unidirectional. Okay, and then if you click on the analysis tab, you're going to select 3D orthotropic. Notice that there is 2D orthotropic, orthotropic 2D, and orthotropic 3D. Okay, so I'm going to use the 3D one. Notice that there's 9 numbers that you have to you have to plug in, and I'm going to do that. Let me see. The 9 numbers that I'm going to plug in are going to be. Bear with me for a second. I'm looking to my other screen. Okay, so this one for Young's modulus here in the x direction, I'm going to have 2.01 GPa, big G, big P, A, so it automatically converts it to Pascal, puts it 10 to the. Oh, I'm sorry. What I wanted was 20. So let me try this again. 20.11 GPa. GPa. Okay, that's better. The next one is going to be 12.04 GPa, big G, big PA. Okay. The next one is going to be 10, 10.16 GPA. Okay, so these are the normal moduli, Young's modulus. Okay, Poisson ratio for this one is going to be 0.532. For the next one is going to be 0.307, 0.307, and the next one is going to be 0.203, 0.203. Okay, and then I need 3 shear moduli. So this one is going to be 8.237 GPa, 8.237 GPa, big G, big PA. The next one is 3.34 GPa, 3.34 big G, big PA. And the last one is going to be 3.373, 3.373 GPA. Okay, so so these are the 9 numbers that I need in order to define any 3D orthotropic material. So we say okay, You know, it's always a good idea to check this thing. So composite, cured thickness 1 millimeter, analysis, the 9 numbers, and we say, okay, now we're going to save this. I'm going to save it in that same folder, and it was not here. I think it was video right there in 3D folder, and I'm going to call this thing, just so that I can recognize it later, 3D ortho. Okay, good. So let me close this and show you that in my folder I have the original part that I created and the 3D orthotropic material that I created. Okay, so let's go ahead and open our part, the one that I created earlier. So it was this one. Okay, so now we're going to go to the composite design. All right, and first I'll create our parameter, composite parameters, add a material. Now obviously I have to go to that folder and retrieve that, and it was on 3 desktop, way down here, right there, and 3D orthotropic. Yep, this is the material that I created, and we say okay. Now for rosette, add a rosette, and there's my rosette. Okay, and say okay. Laminate or directions 45 and minus 45 already default, so I don't have to do anything. Okay, so we're going to do a manual ply here. So we're going to create a ply group right there, ply group. Surface is right there. Draping direction, I always have a habit of doing upward, and we say okay. Rosette was automatically picked, and now first ply right there, which goes into that ply group. The boundary of it is that sketch. See that? This is the sketch. Okay. And the attribute, obviously material was picked properly. Minus 45 is the first one, the bottom one. And do another one. Here's my first ply. This is my first ply. Let's do another one. Yeah, in the same group. And the boundary of it is again that same edge. You can do it from, this is what I'm picking right now is actually the boundary of that other ply. If you want, you can go and select it from the sketch. Sometimes that may be more convenient. So attributes, this one is 45 degrees. Okay, and you can always check it out. First of all, yeah, you can always check it out by ply exploder, and there we are. Apply. So these are the two, 45 and minus 45. Yeah, so see the bottom one is green, minus 45. The top one is red, which is the 45 degree. Okay, good. Cancel that, I don't need it. Let me also hide my rosette. All right, very good. We're done as far as this is concerned. So let's save everything. Now we're going to go to our advanced meshing tools, because we're going to mesh this thing with shell elements. Okay, and surface measure right there. You see that surface measure? You select that, 10 millimeter by 10 millimeter. So there's going to be 30 this way and 10 this way. Okay, and then mesh it right there. This is how you measure it. The other one is just specifying the things, parameters. Okay, this is done, and exit. All right, so let's go ahead and to our generative structure analysis, and let me first hide some stuff that I don't want. I don't want to see my stacking of the plies, stacking plot. You know, it's still there. You can see these different colors here. Those are the plies. So I'm going to hide it. And then I also hide my sketch. This is my sketch. I'm going to hide this because I don't want to, accidentally try to put something on the sketch. Actually, it won't take it, but okay. So here's the clamp. I'm going to clamp this, and I'm going to apply a what is called line force density on this, which is 10,000 Newton per meter in the x direction, positive x direction, which is right there. You can see that. Okay. All right, good. If you say, can I apply force? You can, but in composite, these are usually force per unit length or moment per unit length. So why not do that from the beginning? Okay, good. The only thing I have to do is import my property, import my composite property. Now remember, this was a 3D. Just remember that. Okay. So the support is right there, the face, and I'm going to do it by ply. So click on the wrench and go and select the ply group that I created right there, and it picks both plies, of course. And make sure you symmetrically place it above and below this thing, so that box is checked. We have talked about these things in the earlier videos. All right, let's go ahead and run it. Hopefully I didn't forget anything, and I don't think I have. Done. So if you say, show me the deflection is going to be, this is going to be twisting because of the nature of the stacking sequence, uh, and the nature of the loading is going to twist. So as a matter of fact, let me show you. There it is. And 0.831 is the maximum amount of movement of this coordinate and that coordinate millimeter. Now, I'm not going to generate these plots for you, but I want to show you that this is the one that I'm just showing you. So I'll come back to those things later on. I'll just show you how to plot the stress. To plot the stress, let me go ahead and go there, right click, generate image. Under stress, select the full, full stress tensor, nodal values. You say okay. Now you will get something like that, and you might say, what the heck is this? Now we have talked about these things in the earlier videos, I don't know, 2 through 5, 6, whatever. That's because this stress, first of all, let's see what is it that we are plotting. It's very important to know what this thing is. So you double click on the tree and say, show me what this thing is. Tell me what it is. Well, it's ply 1, lamina 1, the bottom one, and it's showing you C11. C11 means sigma 1, 1, but the 1, 1 refers to the local coordinate system for the shell, okay? So over here, that local coordinate system, the 1, which you think ordinarily is like that, for those elements is actually sideways, horizontal. So 1 and 2 are reversed. To correct that issue, you go here and say, don't show it to me in the local coordinate system, show it to me in the global coordinate system. Global coordinate system. Now that's a lot better, okay? So this is sigma x along the x direction for lamina 1, okay? And what I have here in my slides is this one that I'm showing you, global coordinate system. So I'm not going to come back to those anymore, but I just want to show you how you generate these things, and then we come back and discuss it later on. If you say von Mises, okay, this is the von Mises, and what I'm showing you here is actually, in a minute, is going to be on the von Mises. So I didn't plot it for the entire panel. I did plot it, but only for the piece in the middle. This means that you're going to have to create a group and then just show the von Mises stress only for that group. Please watch the earlier videos to see how you do things like this. That's not really not the focus of this particular video segment. So fine. So let's save everything here. File, save management, the analysis. The analysis is right here. Save as. Okay, it's in that right folder, and I'm going to call it 3D ortho. In case we ever have to come back to it, of course I won't, because I have my slides. I'm going to go there. So we say okay, and we say okay. So we close this, and we close that, and now we're going to create the 2D model. Okay, so now we're going to create the 2D model. Let's start another one. I'm sorry, this is a repetition, but it's something that's worth looking at. Okay, so this I'm going to call 2D ortho. The first part of it is exactly what we did before. We go to generative shape design. We draw that rectangle. because the geometry is the same. That hasn't changed. But I decided to do it so that nothing is left out here. So this one is 300. This one is 100. And the length is this. That is 300. These steps are all identical to what you did earlier. Exit and fill it, F-I-L-L, right there. Okay, join it. Flip the arrow so that the normal to the shell element is up. You can see the coordinate system for elements do make a difference when it comes to displaying things. You just saw that weird thing at the two ends. So this is when I have a better idea of where the normal to the shell is. Normal to the shell is always opposite to that joint thingy. Okay, coordinate system, the one that I screwed up with the first one. So right click, create a point, and minus 30. I'm just going to put it there. Uncheck that. Very good. Okay, so this is done. So we save it. File, save management. This is the 2D ortho part. Save as. Don't do it in this folder. Go to the right folder, which is the 2D one, and save it there. Now I have to do exactly the same thing with material now. So I'm going to close this. You don't have to close it, but I'd rather do that. So you go to infrastructure, material library. Remember, this is the new one that we are creating. So double click on it. First of all, the name of it, I'm going to call 2D orthotropic. 2D orthotropic. Okay, or ortho. Yep. Uh, and then see if you say apply, it changes the name right there. If you say composite, uh, well, unidirectional, 1 millimeter cube thickness, because you want to solve the same problem. On the analysis, now I'm going to go instead of 3D to 2D orthotropic material 2D. Now notice that here I have 9 numbers. Sorry, not 9 numbers. I have uh, 6 numbers as opposed to the 9 that I had before. But we're going to use exactly the same thing. In other, whatever I put for longitudinal in the other one, I'm going to put it right here. And I believe that was 20 point, bear with me for a second. Okay, so uh, the same thing that I put in the Young's modulus for 3D, I'm going to put it here. To 20 point, I think it was 20.1 GPA, big G, big PA. Okay. The next one is transfer. So I use exactly the same number that I had there before, which was 12.04 of big G, big PA. Oops. Let's try it again. 12.04 big G, big PA. I think I put a comma instead of a point. Oops. What happened here? Try it again. 12.04. Yes. Big G, big P, and A. Good. Poisson ratio in the XY plane, I use 0.532. Okay. Now it doesn't have the Poisson ratio in the other two planes, so that's okay. Shear modulus in the XY plane, I use 8.237. 8.237 big G, big PA. Shear modulus in the XZ plane, it was 3.34 big G, big PA. And shear modulus in the YZ plane, I use the same number, which was 3.373 big G, big PA. Nothing else. Okay, so we say okay. and we're going to save it in my folder, not the 3D folder, in the 2D folder, and I'm going to put the prefix 2D orthotropic, just so that I know where it is later on if I need it. Okay, close that. So now we're going to bring our part back. Okay, so we're going to go to the composite design parameters right there, composite parameters, add a material, and to that desktop, and down here videos 2D. This is the one that I just created now. You select this, you say OK, and you say OK. For directions, we already have 45 and minus 45. For the rosette, we select the same one. Okay, good. So why don't we save this? As for, this is the composite parameter. Notice that it is using 2D, not the 3D one. Okay. Now we're going to go create our plies group. That is the surface. And that's pretty much it. Now we're going to create our plies one by one. So manual ply right there in that plies group. And the boundary of it is that sketch, just like before. And the attribute material is 2D, and minus 45 as for first ply. Another one in that plies group. The boundary is still that same thing. You can use the sketch, or you can use the boundary of that ply. It doesn't matter. Material is correct, and the attribute is 45. Okay, good. So we're done here. Save everything. Now we're going to go to surface measure. So where is that? The advanced meshing tool. Click on the surface measure. Select the surface. You know what I did? I think I forgot to join that because I wanted this thing to go up. So cancel that for a second. I think I forgot to join my material, or something didn't quite work. So let me try that. Let me go back here to. You should be able to do these things because things happen. Yeah, I wanted to flip this. Okay, and go back to my advanced meshing tool. Okay, so surface measure there. Okay, and same size element, and now mesh it. Okay, and exit. All right. So we're going to go to our now we're going to go to our generative structure analysis to apply the loads, the restraints, and import the composites. Why don't we save this thing? File, save management. There's the analysis, and I'm going to put in that same correct folder, which is 2D. And just in case I have to go back to it, and I can distinguish it from the other one, 2D orthotropic. I don't have to go back, but because I already have got all my results, put it in the PowerPoint, and I'm going to show you later. Okay, well, let me hide this rosette. I don't want it. Okay, so make sure you hide the stacking plot, and hide the sketch. There's the sketch. You can see that the sketch is that white thingy. Okay, did I hide it? Okay, good. Now when I select the edges, I can select them individually. Before, the sketch was sitting there. That's why every time I selected the entire rectangle. Okay, so this is clamp, just like before. The load is line force density, exactly the same number. The only difference between these two runs is that one is using 2D property, the other one 3D property. And import the composite property. But we are doing it by ply, so to select the surface, the support, and wrench, and then go and select the ply group right there. See that? One ply group selected, and place it symmetrically. And let me run this thing. I think we have everything here. The only thing I'm going to show you is the deflection here. It's going to be exactly the same thing as before, 0.831 millimeter. Right there, 0.8. So there is absolutely no difference, at least as far as the shape goes and as far as these numbers goes, when I use 2D or 3D. So now I'm going to go to my slide presentation. Okay, so we stopped here. We stopped there. And I showed you the result for 3D. This was the deflection, 0.831. And I showed you how to do the plots for stress, just like I did for 3D. Uh, and I suggested that you use the local, global property for the stress instead of local one, because if you use the local one, everything looks good except over here, these ends, you have some weird stuff happening. That's because for elements down here, direction 1 was like that, what was in the y direction, and for the so flips basically. Here I have C22. That means stress in the y direction. Remember, this is global, associated to global. Y is going like that, and this is the shear stress that I showed you. Okay, now I also zoomed into that particular section using the 3D group. And I didn't show you how to do groups in this particular video, but I've done it many times before. Please check the earlier videos 2, 3, 4, stuff like that. And so I'm looking only at the stress in this corner, because at the ends we have end effects, because here you're clamping things. So exactly this clamping affects the stress distribution there. So anyway, I look at this section C11, C22, and torsion. And even for ply 2, these were all ply 1, except for one of them I did for ply 2. And notice that actually these two are identical, except for the sign. Identical, well, yeah, except for the sign. You can see the flipped, okay? Now, I also did the von Mises stress for ply 1 and ply 2 in the middle section. They are identical. Okay, now the result for 2D, the difference was, is instead of 9 numbers, I had 6 numbers. And these 6 numbers, I picked them so that it corresponded to what was done for the 3D one. I'm sorry, these are identical stuff. I mean, I just showed you that this plot is going to be identical. Numbers are going to be identical. You can check that yourself. Exactly the same number as 3D orthotropic. Exactly the same number as 3D orthotropic. Exactly 3 number. So look at what happened here. This was the 3D orthotropic table. This was the 2D orthotropic table. And I took my number here and put this guy in it, corresponding on the right side. Poisson ratio, I don't have this, we don't specify that in the 2D case, because you're assuming plane stress condition. If you go back to some theoretical derivations of composites, and this is the shear modulus. We don't do the Poisson ratio and shear modulus in the YZ plane. We don't use these. That's why they don't go there. Okay. So conclusion. When using shell elements in Catia for composite FEA calculations, it doesn't matter whether you use 2D orthotropic material specification or 3D material specification. You will get exactly the same numbers. These were done with Catia V56, release 2018. If you have other versions of it, other releases, particularly the older releases, 4 or 5 years old, there may be minor changes in the dialog boxes, and but you can handle. All right, good luck. This was always a mystery to me, but not anymore. I hope it's the same with you.